So good morning everyone. My name's Gopal, as Jesse introduced me, and I'm here today to talk to you about LinkedIn's journey of making its economic graph accessible via GraphQL. Before we start talking about how we made it accessible, let's talk about what the economic graph is. If you go on linkedin.com and load up your profile, it's a graph that shows up with a bunch of interconnectedness. For example, you're a member on LinkedIn, you've had a few jobs, you worked at a few companies, their logos show up. So this is essentially the economic graph, a bunch of entities that we are putting together to provide a product. So you can imagine that there are individual entities like member, like job, company, and things like that. And there's a lot of interconnectedness between them. Members go to certain schools, jobs require certain skills, etc. So essentially, the economic graph is a digital representation of the global economy. And we have some impressive numbers: 645 million members, 35K skills, 30 million companies, 20 million open jobs, and 90K schools. And there's a lot of interconnectedness between these entities. A lot of products use this interconnectedness to deliver some value. So how do we today serve out the economic graph? So let's look at our current tech stack before we look at how GraphQL can help us. So we have all of these entities. All of them are served in isolation. So there is a backend service serving each of these entities. These backend services have certain rules. They cannot make sideways calls. They don't talk to each other. Someone else has to put them together. They enforce data access policies. So members have settings on LinkedIn.com. They say my last name should not be visible to non-connections and things like that. So we have to enforce those data access policies before we return the data. Also, they manage the data lifecycle. If a member is added, member leaves the platform, there are a bunch of actions you have to take, like deleting the articles they've written and things like that. So, but when you go on LinkedIn.com, you still see a connected graph. So who puts these backend services together? We have a bunch of what we call mid-tier services that put these entities together and present them to front-end APIs, which you eventually see on the UI. So these mid-tier services join all of these entities together, and not only do they join, they might have to enforce some more privacy rules, some data consistency rules, and things like that. What's more, we have nearline streaming infrastructure and offline infrastructure that follows pretty much the same template. They have some products that need to deliver value. They have to put entities together. So they do. And they also enforce some data consistency and privacy rules. So you can imagine that the code across these platforms is kind of distributed. You have the same code perhaps written in two places. Privacy rules have to be kept consistent between these two places. And a lot of code might get repeated. So we went in search of what would be an ideal solution from where we are. The first thing we wanted was traversal as a first-class citizen. We have a graph. We want to traverse it. Second, we want it to be expressive. Writing procedural code, imperative code is really expressive. You can come up with an API for doing pretty much anything. So whatever solution we choose must retain that expressiveness. Third, we already have world-class infrastructure. We didn't want to build new infrastructure. So we want that solution to easily integrate with whatever we have. Four, since we have all of these platforms and we want the same code to be executed across a lot of these platforms, we want whatever solution we choose to be portable. Finally, it should be easy to use, which means that if you see a query, if you see some code, it should be easy to understand, extend, maintain, etc. Turns out that GraphQL satisfies all of these requirements. Traversal is a first-class citizen. With some OpenCRUD extensions where we use where operators, it's as expressive as a REST API. It's a specification, so we're free to implement it however you like, integrate it with our systems. It's also declarative, which means it's portable. We can port it to any platform, and that platform can do whatever is specific to that platform. Finally, it's quite easy to use. If you see a GraphQL query, you know exactly what it's trying to say. So what we do is we use GraphQL with OpenCRUD extensions, and we use it currently for writing our queries and for also modeling our data access policies. And we'll come to this. This is the interesting part of modeling how data can be fetched and we don't show data that we shouldn't show. So let's work with a use case throughout this presentation. It's a simple enough use case. We want to fetch a particular member's first name. We want to fetch all the positions they've held, the titles of the positions they've held. And we want to respect the settings of the member. So before we start writing queries, let's look a bit more at how we model our GraphQL types. That's when we can start writing queries. So today at LinkedIn, we use RESTly and Pegasus. We use Pegasus for modeling. And the Pegasus is very expressive, has a lot of types, and LinkedIn engineers are used to writing models in Pegasus. Our platforms are used to Pegasus. So we didn't want to change that. So where do we go from there? What we did was we wrote a function that takes in a bunch of Pegasus types and converts them to GraphQL types. There are a few challenges with this, like handling namespaces, handling some type gaps. For example, Pegasus has maps, GraphQL doesn't, things like that. But largely, this works. So to go through our use case, let's model a few entities. Let's start with a member. A member is simple in this case. The member has a unique ID. They have a first name. They have a last name. And you can see that the output GraphQL on the right is pretty much similar. It's just saying that things are required or optional and things like that. But there's an ID, there's a first name, and there's a last name. This model is a little bit more interesting. We have a model for a position or a position that a member has held. It also contains a unique ID. It contains the title string. And interestingly enough, it contains a reference to the member, which in the Pegasus model, which is on the left, it's a long. It's just a reference. But we have annotated it. We have said that its relation name is position. Its entity that it's related to is member. And cardinality is many, which means that one member can hold many positions. So some interesting things happen on the right. One is that in position, member is no longer a long. It got resolved to the actual entity, which means we can now traverse from position to member. Also, we inserted a reverse edge into member so that we can traverse from member to their positions. And you can see that it's an array of positions because a member can hold many positions. The final two models that we're going to look at is member settings. Let's say that the member has a setting called truncate first name, which is a Boolean. And what we do is we then insert that settings as a type into member, and you get the final member type, which contains an ID, a first name, a last name, the settings that they have, and the positions. So we are well set up to now talk about queries and data access policies. Let's look at our user query. What we said was we wanted to fetch a particular member's first name. We want to fetch all the titles they've held, but we want to make sure that their settings are honored. The user query is quite simple to write. You have a profile. You want the member whose ID is some member ID, and you want their first name, their positions, and the title. Now let's look at the data access policies. How do we respect the member's first name settings? What we do is we model data access policies as user-defined functions, but these are pure functions that declare their inputs through GraphQL. What does that mean? Let's look at the first name access policy that we want to use. We want to show the full name if the member is viewing their own profile, or the member has said it's OK to show their full first name. If neither of this is true, we want to truncate it to just the first letter. So how do we express the input to this user-defined function? It turns out that we can express it via GraphQL. So if you look at the GraphQL query on the right, it's saying exactly what we said in English. It is saying, show the member's first name if the ID is the same as viewer ID, which means the member is viewing their own profile, or if their settings say that it's OK to not truncate their first name. So this UDF is using this GraphQL query as input. Now let's look at the UDF itself. It's a pure function. It's receiving the raw value of the first name, and it's receiving the access policy result that it just defined. Putting these two together, it can determine whether the first name should be shown or it should be truncated. So the code in the actual UDF is quite simple. It says, does the access policy result contain a key called first name? If it does, return the first name as is. If not, truncate it. So we have now defined models, we have defined queries, we have defined data access policies. How do we go about executing this query? So executing the queries takes a bit of putting a lot of stuff together. For one, we want to merge the user query with the data access input policies, because there are a lot more opportunities for optimization in that case. We want to optimize the queries once we put them together. Third, we have a lot of disparate sources. For example, we have our in-house document store called Espresso. We have a bunch of REST APIs that serve source of truth data. We have other systems like Venice, which store derived data, etc. So we want to be able to fetch from all of these derived sources. So what do we use for executing? Here's where Apache Calcite comes in. Apache Calcite is an open source Apache project, which basically is a SQL database kind of engine where you plug in your own adapters. So how does this work? It provides an abstract representation of your queries called a query tree. It provides a query optimizer. it also provides some execution engine artifacts, like it knows how to filter, it knows how to project, it knows how to sort, aggregate, and things like this. Finally, it also provides the ability to put in pluggable adapters. You want to talk to your own store? Sure, write an adapter to do it, and it works. It's just an interface that you have to conform to. So now let's go through the cycle of executing the user query that we just got. So first thing we need to do is parse that GraphQL query into what Apache Calcite will understand. So what we want to do is take a GraphQL query that comes in and put it into the Apache Calcite representation. So we'll go through this exercise for the query and the data access policies, because both of them are GraphQL queries. So how does the query tree for the user query look like? So this query tree is quite simple. It says scan member, use a filter on member because we've asked for a particular member, project the ID and the first name. Though the query only asked for first name, it turns out that we need the ID to do some joins. Then we also scan positions, and we project the title and the member. And again, we need member because it turns out we need to join them together. And finally, we do a left outer join of the member's ID with the position.member. So simple enough. The data access policy is even simpler. It says scan member, and there's a bunch of conditions, which is the data access policy, and project the first name. So now we have two query trees independently for the user query and the data access policy. Now we need to put them together so that we can optimize it and look for opportunities to not make the same downstream calls again and again. So here's what we start with. These queries are unchanged. On the left is the user query. On the right is the data access policy. We want to put them together. The first thing that happens is the data access policy gets an extra projection. It didn't have an ID projection, but we just put in one because we want to join it with the scan of member that already exists. And how does that work? We just do a left outer join. Now what happens is the query result that comes out will contain both the raw first name and the first name that came out as a result of the access policy. So the scan of member on the right may or may not have the first name, depending on what the data access policy said. So now we have a one giant merged query, and we have to go ahead and execute it. So there's a lot happening on the slide, so we'll break this down and see what exactly we do to execute stuff. The first thing we do is we push down filter predicates. It turns out that we know that we want to scan a particular member, and we also know that member has been joined with another member, which is a self-join, and we know member.id equal to m2.id. This means that whatever filters exist on member.id, the same filters can be transported to member2.id. So we do that. Why do we do this? It's because most of our backends are key value stores. They want a key so that they can look up a value. The previous query that we had for the data access policy just said, for every member, here is the policy, but key value stores want a single member. So we added an extra filter there saying ID equal to member ID and the data access policy. We can do the same thing for position. We are going to a REST API. Without filters, the REST API can't return us all the positions. That's not feasible. So what we did was we looked at the join condition. The join condition says member ID equal to position member, and we pushed that filter predicate down. This is a simple enough query. The filters are available statically. You can move them during planning time. It so happens that there are queries where these filters are not available at planning time, which means that you have to query a certain part, finish a part of the query before you can transmit those filters to other parts of the query. We can do that too. So you can, if this member ID was not available, if we were looking up a member by first name instead, we could actually go down to a search index that gives us all the members, fetch their IDs, and then insert them on wherever they're required. But this is a simple enough query, and we can move them at planning time. Once we have moved all of these queries, all of these filters in, we are now ready to fetch whatever we want. So what we can get data from the REST endpoint. We can get data from our Espresso and our Espresso document store. But we are querying member twice and with the same ID. So it doesn't make sense for us to go to Espresso and ask it again and again for the same member ID. So we insert a per query cache that knows what we have already asked for and then returns that data as is. This query cache is only for a single query. If you make this query again, the cache will be removed and there will be another cache that comes in just for that query. So we can retain read after write consistency. If you change your profile on linkedin.com, you want to see the latest thing. You don't want to see some cached version of it. After we execute all of this stuff, we have an output, and the result set, which is a common construct in SQL, looks like what is on the top. It's returning the ID of the member, the first name of the member, the ID of the member again, first name of the member again, and then the title and the member's ID. So we have a bunch of result set. That's not how we want to present it to our clients, because they made a GraphQL query, they're expecting a GraphQL response. So we need to do some post-processing. Also, we need to apply those data access policies that we just put into the query. So how does that happen? So on the left is all of the data that we got out from the query. Imagine that there is a member whose first name is Jane, and they've held 3 positions, which is SWE, senior SWE, and staff SWE. It turns out that the result set has 3 rows as output because it's a Cartesian product. But most of it, the first 4 columns are always the same, and the 5th column changes. It turns out that we can collect this into a response that looks like a GraphQL query, because we know that the first 4 columns don't change. So once we collect this, on the right is what it looks like. There is a member whose first name has been populated. The access policy result is also available. So this is not yet ready to send down to the client. And then we have all the positions that they've held. So now we need to apply our access policies. So we have the access policy result. This is exactly what our UDF asked for. So we deliver that access policy result and the raw value of the first name, which is Jane, to this function. So in this example, the member is viewing their own profile. Member ID equal to viewer ID equal to 1. So it turns out that the member can look at their own first name. One of the conditions was members allowed to look at their own first name. So what happens when this UDF receives the access policy result is it can see that first name exists in this access policy result. So it just returns the first name as is, and we have the output. And we can send this back to the client. Let's look at another example. The other example is that someone else is viewing the member. Member ID is 1, viewer ID is 2, and the member has asked for their first name to be truncated. So the output from the result set is slightly different. You'll notice that the 4th column is now null because the conditions failed. Neither was the member viewing themselves, nor were they allowing us to show the first name untruncated. So it turns out that when we collect the response, the first name access policy result does not contain the first name anymore. And the UDF now knows what to do. It knows that the first name does not exist in the access policy result, so it just truncates the first name. And here's the output. You get first name just J. Right? So we do all of this post-processing so that, and there are a bunch of things that we can do. Each of these fields that we have, first name, last name, etc., can have their own data access policies, and we merge them. And it also, the good thing about this is since GraphQL, you project exactly what you want, you don't apply data access policies on the things that you didn't project. So this naturally lends to what we want to do, which is don't call things that we don't want to look at. The third thing is that this sort of construct can be used for a variety of different things. Here we're using for data access policies. We also use it for derived data. For example, the member might contain a full name. We don't want all of our clients trying to compute a full name. Instead, we offer it to compute it for them. And it turns out that it can be modeled exactly the same way. You have a GraphQL query that says, give me the first name and last name, and a UDF that concatenates them together. So all of this derived data, data access policy result, you can express that through GraphQL queries and a UDF. So now we come to the question of portability. We have all of these nearline and offline infrastructure that needs all of this data. So we are working on making the UDFs themselves portable because each of these platforms has their own requirements of what format the data should be delivered in, what's performant, etc. But today we can convert some GraphQL queries to SQL and Spark SQL. So what happens is somebody defines a query and all the data access policies, and we can convert that into Spark SQL and run it on Spark. And all through this exercise, the people who define these entities, member, company, they only have to write code for their UDFs. They write no other code. They just provide us some models and some data access policies expressed as GraphQL queries and a bunch of pure functions. And we know how to put this graph together, make it privacy compliant out of the box, compute derived data, etc. So the amount of code that is rewritten or duplicated is almost non-existent. And these GraphQL queries and these UDFs work on all platforms, so you don't have to write the same thing across platforms, worry about keeping these platforms in sync, etc. So Calcite is also is a helper for all of this, because Calcite's query tree representation is very, very abstract. So you can turn that into any declarative language that you want. So here's how we're extending to nearline and offline. So that's it from me. You can talk to me after this presentation, or there's my vanity name on LinkedIn, VGKHOLLA. We're also hiring, so you can look us up. And if you're interested, we'd be happy to talk to you. Thank you so much.